Okay. Thank you very much for being here, and thank you, Ying, for the invitation. It's really a pleasure and an honor to present here today. Um, I'm currently a postdoc at the NYU Grossman School of Medicine. I'm going to be talking about recent work on identification and estimation for mediation analysis in longitudinal settings. Um, and I have some co-authors on this work who I'll talk about towards the end. So our scientific context here is looking at data from a study of the way patients were treated for coronavirus at the beginning of the COVID-19 pandemic, when treatment guidelines were sort of up in the air because it was obviously an unfamiliar course of disease. Um, in particular, one of the major dangers of uh, COVID-19 is the development of acute respiratory distress syndrome, or ARDS, which causes difficulty breathing due to fluid buildup in the lungs. And to treat this, physicians often implement invasive mechanical ventilation, which is basically supporting respiration through the insertion of a tube into the airway. Um, it's been found that IMV, invasive mechanical ventilation, can uh, increase the likelihood of developing acute kidney injury or the sudden decrease in kidney function. Um, I'm not sure the extent to which it's totally mechanistically understood why this happens, but it's been observed and is the subject of continuing research. And AKI, acute kidney injury, is also um, a real mortality danger, especially in the intensive care unit. Um, so when we decide how to intubate, when and whether to intubate patients, you sort of have to balance the risk of mortality from ARDS, the pulmonary issues, and the mortality issues associated um, with AKI. And so early in the pandemic, which is the data, we're going to be looking at the guidelines tended to recommend uh, intubating patients relatively early in the course of disease, and over time, the guidelines shifted to intubation later in the course of the disease. So when we think about the research question in particular, we're mostly interested in mortality, and in particular, what's the effect of invasive mechanical ventilation on death among COVID-19 patients, and how much of it operates through causing acute kidney injury. So this is a mediation question, um, talking about modified treatment policies or decisions that change the course of treatment over time uh, for longitudinal data. And there's some recent research from collaborators of mine who are looking at similar questions, but this is the work that sort of puts all these ingredients together. So the basics of mediation analysis, obviously the three main variables in any mediation analysis are going to be the exposure, or in this case, some sort of medical intervention in the treatment, which we'll call A, a mediator variable M, and an outcome Y. And we're interested in the effect of A on Y and how much of it operates through the mediator. And you might have baseline covariates, which we'll call L, that affect all the subsequent variables. And another issue that comes up and can be important is an intermediate confounder, which is affected by the treatment, but in turn affects the mediator and the outcome. And how do we quantify mediation effects? The sort of most natural estimate that we can think about are called the natural direct and indirect effects, which are just averaged over the population for each person the natural direct effect is what happens when you keep the mediator coming from some treatment value, which we'll call A prime, but you allow the treatment, the outcome to vary based on the treatment of interest. So this is where the mediator is coming from some fixed intervention, and the outcome given the mediator is coming from a different intervention. So that would be the effect that's not through the mediator, whereas the indirect effect is the effect through the mediator. So that's keeping the outcome, the treatment that's affecting the outcome the same, but varying the treatment that is seen by the mediator variable. And these natural direct effects formalize the idea of how much does some effect go through the mediator and how much does some effect go not through the mediator. But the problem is that this estimand cannot be identified when there's an intermediate confounder, even if this intermediate confounder is measured. The reason for this has to do with one way to think about why this happens is to look at a structural causal model, in which case when you think about where the outcomes for the natural effects are coming from, they involve two counterfactuals that involve the mediator, the intermediate confounder distribution, one under treatment A and one under treatment A prime. And so you would need to learn the joint distribution of the outcomes under both treatment levels, but you need to learn the joint distribution of the intermediate confounder under both treatment conditions. That's not really possible from observational data. You can learn the marginal distributions, but not the joint distributions. But because you can learn the marginal distributions, you could introduce a different estimand that is similar in flavor to the natural direct effects, but instead of thinking about the specific mediator values that would be seen from each person, or you think about taking a random draw from the mediator distribution for each intervention level. And I think that this is mostly useful in as much as it can approximate the natural direct effect. And there's some recent work about the extent to which it actually does approximate the natural direct and indirect effects. I think it can be reasonable in many scenarios, although it's a matter of some debate. But we're going to be estimating these so-called randomized interventional effects in this study for the purposes of because it's possible to identify from observational data. So then the other ingredient in this analysis is a longitudinal modified treatment policy, which contrasts with static intervention. So a static intervention is for each time point, you explicitly set what the treatment value of interest is going to be. In a longitudinal modified treatment policy, or an LMTP, we're going to allow these values, the intervention, to be responsive to all previous variables, including what the treatment that would have been observed naturally, which we would call the natural value of treatment. So just for example, a simple example would be at each time point, you could double everyone's observed treatment or exposure. Obviously, that's not a static intervention because not everyone would be receiving the same treatment value, and you're allowing it to respond to variables in the study. And so this allows you to model dynamic responsive treatment regimes, which might be more realistic because it's sort of rare. There are only certain contexts where you think about giving the same treatment to every single individual. And from the mathematical point of view, it can alleviate some difficulties that come up when you try to estimate dose response curves, which you need for continuous treatments and static interventions. So if we think about what our structural causal model is going to be for this study, it's sort of similar to the DAG I showed earlier, except there's going to be multiple time points. So at each time point, we'll have baseline confounders L, an exposure A, mediator M, treatment L is the next time point, and between the mediator and the next treatment L, there's the intermediate confounders. And this continues through time point after time point until the outcome of interest. And these big arrows are just representing connections to all subsequent nodes. So it's statistically, it's a nonparametric model. And what we'll be thinking about in terms of a structural causal model. So the first variable L is a function of some error variables, and then the next variables are functions of the previous variables and additional unobserved error variables. And then our estimand that we're going to need to learn is just for any two arbitrary LMTPs, so these are treatment policies, what's the expected value of the outcome where the mediator is drawn from one of the policies, and the outcome given those mediator values are drawn from the other treatment policy. And if we're talking about it'll often be useful to compare some treatment policy to the status quo. So one of these could be the status quo. So this is the randomized interventional direct. This gives you the randomized interventional effects for longitudinal data. And to identify this estimand, it's going to look pretty similar to most ordinary causal inference problems where we have conditional exchangeability for the treatment and the mediator. The HTs here are like the entire histories up to that time point. The only difference in the longitudinal setting is that you need this ignorability hold to hold for the future histories, not just a single time point, but you need to have, for instance, the treatment at a given time point is conditionally independent of the error variables for all the future history variables. Positivity is basically the same as usual, except that we're talking about the positivity of the intervention, the modified treatment policy instead of the entire dose response curve. So it's sort of a weaker assumption than you might ordinarily see. And there just needs to be some regularity conditions on how complicated the function that tells you how to adjust the treatment needs to be. Here we're going to be talking about that the inverse has to be piecewise. It needs to be invertible with a piecewise differentiable inverse. Or sorry, the whole function doesn't have to. I don't think the whole function doesn't have to be invertible, but it has to have differentiable piecewise inverse functions. So once we have this set up, how do we actually come up with the estimator? We're employing the technique known as sequential regression, which is just a way of estimation in the longitudinal G formula. I won't go into details because it's not really a novel part of what we're doing, but it involves regressing the outcome onto previous variables to generate pseudo-outcomes, and then regressing those pseudo-outcomes, iterating backwards in time. And for a modified treatment policy, the probabilities are just replaced with probability ratios. to get at the interventional estimands, all that needs to be done is to fit one model for the mediator values to get a probability distribution for the mediator values under one policy, and then fit another model for the outcome variable with those mediator values under the other policy. Now, what is sort of difficult is that this needs to be fit for every single possible mediator value, so that you take the product and sum overall possible mediator values. And this is a issue that was kind of mentioned in the first talk, which is that this is computationally difficult for if you have many time points and a mediator that can take on many different values because it grows exponentially. But that is the approach we take here. It would be interesting to know if there are better ways of doing that or approximations that could be used in larger studies. And it has a sequential double robustness property. By incorporating the treatment models, you only need to consistently estimate at each time point one of a couple of pairs of variables, where each variable is either the pseudo outcome for that node or the probability model for the previous intervention node. And we have a publicly available R package to implement this procedure called LCMMTP. So returning to the study, we have about 3,000 patients hospitalized with COVID-19 at New York Presbyterian hospitals. It was March to May of 2020, so very early. No prior history of chronic kidney disease. And this is a time when, again, doctors were making treatment decisions under a lot of clinical uncertainty about the guidelines. And while this is not desirable for medicine or public health, it can be helpful for causal inference, because in general, doctors make treatment decisions on the basis of observed variables for the most part. So you sort of have a dilemma where if you include all these variables, there could be a lack of positivity. And if you don't include all these variables, there could be a problem with ignorability. And so when you have a situation like this, it's more possible than usual to learn causal effects from treatment decisions. So what we're going to estimate is what would happen, or what would be the difference in mortality if IMV, invasive mechanical ventilation, were delayed by 1 day, or if someone only received it for 1 day, what would happen if they didn't receive it? So we have baseline confounders that are like demographic variables. We have time-dependent confounders, which are the vital signs in the lab results. And the longitudinal increment is 24 hours. What we see is that we have these numbers, if a positive value represents the fact that delaying intubation is beneficial. So we have relatively large standard errors and can't say anything too definitive, although we do see a pretty large indirect effect through AKI, but that's not too surprising. But overall, from the point estimates, this is saying that delaying intubation could be helpful overall. The indirect effect of delaying intubation is helpful, and direct effect of delaying intubation is not helpful. So that sort of confirms our hypothesis that intubation itself can cause mortality through AKI, even if independent of AKI, it can be beneficial for respiration. And this is a situation that's known as inconsistent mediation, where the direct and indirect effects operate in opposite directions. So you could think about how to use this in practice to actually inform treatment decisions. One way is if you have a way of estimating conditional effects, you could think about for whom the direct effect would be harmful, and then maybe you wouldn't want to give them the treatment at all if you're pretty confident that the indirect effect is also going to be harmful. Now, you could just skip this and estimate the total effect, not think about mediation at all. But AKI is actually a condition for which it's possible in theory to remediate through external treatments. So this allows you some more flexibility in the way you think about treatment decisions. And if we do an analysis where basically we try to get a heuristic estimate of the conditional average treatment effects by regressing the influence functions on individual variables, this is definitely not powered enough to provide real guidelines, but just sort of an exploratory analysis. We find that nothing jumps out too much, except that the biggest effect seems to come from ILD or interstitial lung disease. This is saying that delaying is harmful for direct effect, which makes some sense if someone already has pulmonary issues. They might require intubation more urgently than other patients. So to conclude, causal mediation analysis is complicated with time-varying exposures, mediators, and confounders, though a lot of existing frameworks can be sort of combined to yield a reliable analysis in this setting. And this mediation analysis can aid clinical decision-making and scientific understandings of causal mechanisms. And in the specific case of COVID-19, we've highlighted possible inconsistent mediation through acute kidney injury on mortality. So I want to thank my co-authors. My postdoc advisor is Yvonne Diaz of NYU. I'm also advised by Kara Rudolph of Columbia. Edward Schenk is a physician who provided us with the scientific context. And then Kat Hoffman did most of our data analysis, and Nicholas Williams wrote our R package. Some references and a link to our archive paper. I'm sure we'll also be able to provide it through the seminar website. But thank you very much, everyone, for your attention, and I'm happy to take questions.
Thanks, Brian, and thank you for being so good with time. We do have a few questions. Kara is actively answering some of them, Kara and Nick. But one of the questions Kara suggested that it would be good for you to perhaps answer live for us. So the question is the following. Based that you consider longitudinal model, can your approach be used for longitudinal structural equation or graphical causal models, such as cross-lagged panel models or similar?
I'm not familiar with the specific model of what exactly a cross-lagged panel model is. However, the model that we're using is a non-parametric structural equation model. So I would believe it should be general enough to handle most settings, although if it imposes other restrictions on the data generating process, it might not be the most efficient way to handle them.
Thank you. And maybe we can take one more question since we have time. This one is by Michael Shoemaker. If there are multiple mediators per time point that are separated by confounders, then in principle, one may have to fit more than 2 models per time point, i.e. for each mediator block and the pseudo-outcome?
The model that you have to fit is you have to fit a model for every possible longitudinal mediator value. So if you have like n time points and if you have n time points and 2 mediator values, then you have to fit on the order of 2 to the n models to get the probability of each mediator value. If I implied that that wasn't the case, then that was a mistake. It's not just about per time point. It would be exponential in the number of time points. And it is exponential. Sorry, it's exponential in the number of time points where the base is the number of possible mediator values. Hopefully that answers the question.
I think so. So Ying and Ying, I'm also frozen. So sorry about this. My Zoom has been freezing today. Ying, can you help me with more of the questions, perhaps, if we have time for one more question?
Yes, of course. Yeah, so probably can do another question. It's from an anonymous attendee. In the G formula, there is a product between the outcome model and the density of the mediator. In the implementation of the estimator, do you take the product between the predictions of these two terms?
Yeah. So if I'm understanding the question right, the way we combine the mediator and outcome models together is summing for each possible mediator value. We take the product of the mediator probability from the model and the outcome expected value. So they're multiplied and then summed over all the possible mediator values. And I see that Nick Williams has also been typing out answers for these. So he might also be good to ask about specific implementation questions. But I think the answer to that question is yes.
Thank you for answering the questions, and also thank you, Kara and Nicholas, for answering questions by typing the answers. There are a lot of questions from the attendee. So with that, it's a good time to wrap it up. Thank you again, Abby and Brian, for the great talks and for answering the questions. For next week, we will have. Let me share the screen. Is it? Okay, so for next week, we will have Rodrigo Pinto from UCLA, and he will be talking about a slightly different causal language than the graph models and potential outcomes framework. And we hope to see you next week. With that, let me stop the recording.